So this is now my lecture where I will be speaking about diffraction gratings as optical components, and I will provide simple equation known as the grating equation to understand their behavior. So essentially into which direction light is being diffracted from diffraction gratings. And what this gives us, well, it gives us the means to calculate in which direction light is being efficiently diffracted when we have singly periodic structures, so gratings, and this of course can be used as a basis of components where we need to utilize diffraction gratings. And what kind of instrumentation or what kind of functionality we would need then, or we would want to achieve with diffraction gratings is that essentially we will see shortly in the grating equation that now the direction into which light ray is propagating after the diffraction grating, that sensitivity depends on the wavelength. So essentially that gives means to realize highly dispersive optical components. And here highly dispersive I means that I can really easily separate different frequency components of incident light, a broadband incident light, into different directions. So then for example, a green color of light would go in a different direction than red color of light or blue color of light. So this is the kind of functionality that I get out from diffraction gratings, and this is something that is very different from most of other components. So of course we could realize similarly you could use prisms to as dispersive components, and there we would be taking use of the dispersive nature of the glass, the material refractive index of the glass that is dispersive, and then we would see that the different frequency colors or different frequencies of light, different colors of light would actually propagate slightly in a different manner inside the piece of a glass, and then in a prism we could utilize this to separate different frequency colors into different directions. But with diffraction gratings, the same thing can be done, and in more simple manner, cleaner manner. And the nice thing about this is that they can even, in fact, engineer the properties of these components quite a bit by just utilizing or changing the periodicity and the kind of periodicity profile of my grating structure. But more on that, of course, in the actual lecture. So this is what I will be speaking about in this one. So diffraction gratings from the kind of more component point of view and not the mathematical point of view as we were discussing in the previous lecture. So earlier we saw that the light gets diffracted when we have it incident on a periodic grating. So we are considering in the previous lecture a periodic arrangement of single slits. And now what happens, of course, is that we have interference effects, and that gives rise to diffraction of fields. And now the interference is such that instead of a single feature, single irradiance pattern that is being affected by the diffraction, we now actually saw the emergence of many diffraction peaks. And this is now what we will be looking at from a more qualitative point of view, that what happens, because that can be used to understand how diffraction gratings as components, how they behave. And either way, like we can think that diffraction gratings, either they work in a so-called transmission configuration, so they basically transmit incident light, or it could also be that they would reflect light, and this figure will be shown in the next figure. This figure that I'm showing here in this slide is showing me a transmission grating. So we have an incident light where we have a periodic arrangement of my slits, and in fact it doesn't even have to be a slit so that it would be totally through the component, but rather just kind of a corrugation, periodic corrugation of my component here. The key thing here is that we have some kind of slits, and we have them periodically arranged so that we will see constructive interference taking place in a very specific directions. And then when these right directions take place, their constructive interference of light takes place, and then we really see irradiance distribution forming there. And in between we have destructive interference, and no light is being basically propagating along these directions. So this is how a transmission grating works, and gratings in general, how they work. So essentially a diffraction maximum, we get that formed when the waves along this certain direction, when they all exhibit a phase of a 2 pi integer. So this is the basic condition. So essentially we require constructive interference to take place, and this is what then dictates into which directions we actually see light formation. And if you're interested about the full details of the math, of course, check out my previous lecture and where we did the derivation for a single case scenario of having a slits arranged periodically with the periodicity of B. And this, incidentally, is my picture showing a reflection grating. So now I have my incident wave, and this would be the 0th order. So essentially the incidence angle theta I will be the same as the reflected angle. And then we also have other diffraction orders labeled with the different m's, and these m's indeed correspond to the integer, giving us to a multiple of 2 pi. So the mth diffraction maximum, this is also called as the mth diffraction order. Please note the terminology here. And if we would want to change the cross-sectional profile, and of course we calculated this in our previous lecture for the simple case of a slit, then we could do a lot of tricks, a lot of engineering, and then we could, for example, make things such that only specific diffraction orders would be present as an outcome of my diffraction grating. So basically, for example, I could make it such that for example, m equals 1 diffraction order would be emphasized and the other diffraction orders would be diminished. So these kind of features and feats would be possible if we would be designing the grating structure accordingly. And this is nice because if we would want to, for example, get a high performance component out, it might be the case that we only need to look into a given specific diffraction order and not the many of those. So this is indeed when we would be playing these kind of tricks. So we would be basically placing the grating structure, and then we would be speaking of placed gratings. And graphically and in physically and engineering point of view, what that means, blazing of a grating, that we change this cross-sectional profile. Here we just have a single periodicity and a single rectangle function giving rise to me of the diffraction. But now if I would be, for example, having a triangular shapes here, I would be getting a different kind of irradiance distribution. And in fact, I could also introduce several periodicities into the structure, and that would give me possibilities to control into which directions I'm actually getting a more diffracted light and in which directions I'm actually diminishing the emission. So these would be the tricks that I would need to do if I would be looking more into improving the performance of my diffraction grating. So please note that there are these kind of possibilities when using diffraction gratings. And let's now just find quickly the kind of condition where the diffraction maximum takes place. So where the 2 pi integer is a valid condition. And for simplicity, of course, the same thing applies for the reflection grating. We just consider here a transmission grating, but in the end, it doesn't really matter. And we have a periodic structure, so we have a periodic problem. We really can just go on by just requiring, go on their derivation by requiring that the phases of the waves that pass through identical points of the adjacent slits. And now I'm assuming that I have a periodic structure here. I'm looking at a point, for example, in here, and I would be looking at the point here. They are basically identical points because I'm assuming that I have a periodic grating. Then I can require that there will be basically a basic specific phase. They should have the same phases when we have the wave passing through these identical points, so that we cannot really distinguish between the phases between them. And that means that the phase change should be an integer of 2 pi. So essentially 2 pi m, where m is an integer. And this is what we require and what arises from the periodicity of our problem. So here also, when we look at the observation point or direction, we would also require that, okay, if we need to have constructive interference in these different directions, then definitely we need to also be having the condition of 2 pi m fulfilled so that we have constructive interference in these different directions. And these are now used as the basis to understand the diffraction, into which directions light is being diffracted from a grating, and soon we will be getting the grating equation out of this derivation. So let's look at the geometry more specifically, and then really look into vicinity of two slits or corrugations. And of course we have a periodicity in our system, so this would be in like 1 point, and this would be the adjacent identical point D here, and then the periodicity of my grating, let's denote that with A, and then I'm having my incidence angle theta I here, and then I have my reflection angle theta m here, and I was considering transmission grating, so this is fine, this works. So now what we need to do is that we need to calculate the optical path difference, because of course that allows me to calculate then the actual phase difference when I'm multiplying that with the wave numbers amplitude, so the k term here. And now I can simply look at the figure and I can calculate the optical path difference between two different lines. So essentially what I need is that I will need to look at the line of AB here. So this is the kind of phase accumulation for this ray of light, and I'm looking into this line, and then I'm looking at the scenario that light is being incident here. And these points, they are identical points, so they should have a 2 pi m phase difference, or they should have similar phases. And then I'm looking at the ray of light going into the diffraction order. And since I'm looking at the constructive interference, then the phase difference should be a 2 pi m here. So basically I'm taking a line that is perpendicular to these outgoing rays, and then this is what defines my problem. So essentially I must calculate the optical path length difference between the line AB and the line CD, because that gives me the kind of phase difference that has been accumulated between the rays of 1 going there and the ray 2 going there. And since it's a periodic problem, we do not need to consider the rest of the rays. This already is enough. And I can look at the trigonometry of things and the figure, and I can land with this equality here. So essentially I can look at the AB distance first. So I want to calculate what is this length here. So essentially I can have this angle theta m here, the refraction angle or the diffraction angle. And essentially this is equal to the angle as in here. And how do we land with this? Well, I guess there's many ways, but I'm imagining myself that I have this angle in a case that I would draw a horizontal line here. So then this angle would be theta m, and then I can draw a vertical line from A to D, and then I know the total sum of my angles of a triangle will be 180, so that then this will be 90 degrees here, and then this line angle here would be then the theta m minus this angle would be equal to 90 degrees. And then I can actually verify that this angle I'm drawing here, or I would be imagining here, that would be the theta m. Sorry, this would be the theta m. And then I can calculate that if I want to calculate the length, I can calculate that by just taking the hypotenuse A times sine of theta m. So this is how I get into this. And then the same thing I can do for the CD line. So essentially I can imagine that I'm drawing a triangle from the point D to A, that would be the hypotenuse. And then I can calculate this distance by just equating that this theta I is actually this angle here. And then I'm calculating the line CD to be essentially A, the periodicity of my grating, times the sine of theta I, where theta I is the incidence angle. So points A and D, basically they correspond to each other. They are identical because we are assuming that our grating is periodic. And A is the period of the grating, and now we can really solve the phase, basically the phase difference, by just calculating that the phase difference is the K, the 2 pi over lambda, times the optical path length difference. And now I can plug in what we discovered for the OPL, optical path length. So that's basically the A times the sines of theta m and minus sine of theta I. And now this gives me the grating equation, because I know that the phase difference must be an integer of 2 pi m. Sorry, it must be an integer of 2 pi. So essentially delta must be 2 pi m, where m is an integer. And now I can solve things essentially for to give me a grating equation. So now I have A, the periodicity of my grating, times the sines of the angles, equals to multiple of lambda, where lambda is the wavelength. And this is basically a grating equation, and what it tells us is that in a given diffraction order and for a given incident wavelength, if I know the incidence angle, I can calculate the different diffraction order into which direction this specific order actually is being diffracted. And I can change the diffraction orders, I can calculate all the different diffraction orders, and I can relate them with the very specific directions. And the same equation, in fact, also applies for the reflection type of a gratings. And the nice thing here, this already I mentioned in my motivation introduction to the lecture, is that now I actually have my grating equation, and we see that the diffraction angles, they depend quite sensitively on the incident wavelength. And we don't even need to require that this diffraction component would have any dispersion, because this is based on the diffraction. So we right away see that we have the lambda dependence, the wavelength dependence here. And this gives me possibilities to realize dispersive components by just using diffraction gratings as components. And this is the neat thing about diffraction gratings, because I can now separate quite easily different frequencies of light to be rays of light that are propagating then in a different direction. And then quite easily I could, for example, come up with a means to realize a spectrometer, so that I would have my broadband source going through the sample and then emit incident on a diffraction grating. And then after the diffraction grating, the different colors would be propagating in different directions. And here in a far field, if I would be placing a camera here, I would be able to detect the different frequency colors, provided that the different colors propagate in a different pixel on my camera. So this, for example, is being used quite a bit in a diffraction grating based spectrometers as a functioning principle of making spectrometers. So you don't even need to do an FTIR spectrometer, that we can even just use a single diffraction grating and a camera to record a spectrum of light. So this is what I wanted to say in my final lecture regarding diffraction effects, and hopefully you know quite a bit about diffraction effects and how that can be used for the greater good of mankind. And I hope you had a good journey. So congratulate yourself. This has been again a long stretch of lectures. So please enjoy the week. Continue doing the homework exercises and reinforce your learning by doing the quizzes we have with the course. I hope that kind of helps you to structure things that we have gone through. And join me shortly in the final set of lectures where we will be discussing about geometrical optics. So I thank you, I congratulate you, many kudos points to you, and enjoy the day, the evening, and the rest of the week. So thanks, and bye-bye.